Hi there, welcome back. Well, we've got things set up for the alignment of the AM IF, which I believe requires it. I can see somebody's messed with these over here. These two still have their wax, which is not to say they don't need tweaking, but we'll just have to see. I did a hell of a lot of research. I read the manuals, I've read instructions, I read about 3 different types of manuals on this, including the one on the T1000. This is the T1000CD, just to get an idea of how they go about it. And I'll describe it very quickly. What they suggest is you remove this point over here from the front end board. This is basically where your RF front end comes in. It goes onto there to point number 6. And ground, and they suggest you connect a signal generator with a 455 kilohertz carrier to that signal through a 4 picofarad capacitor. And I happen to have one here. It's a very small capacitor, which is fine. So the signal goes in there, and it comes out here at pin 9. It's this one over here. And this then goes off to your audio selection switch, where it selects between AM audio or phono audio, and then that goes into your power amplifier and you get your result. So if everything is well aligned and you put in a 455 kilohertz carrier with a 600 hertz or 1000 hertz, in other words an audible tone modulated on there, you should hear the beep or the tone on your speakers. That's fine. However, when I couple the scope to this point is so small that it's very difficult to get a decent reading on the scope. And they're actually describing this as a wobulator setup. Now, wobulator setup is no mystery. What it's doing is it's actually sending a sweep. Let's say you're trying to align for 455 kilohertz. You'll send a sweep from about 435, so 20 kilohertz below, to 475, 20 kilohertz above. And as your signal comes in there, that's just a carrier, it'll produce a signal on the output there. And that signal you would see as a bell curve, and you would adjust it to peak at 455 kilohertz. That's the signal you want to get through there strongly, okay? That is a problem because I don't have a wobulator, and these levels of signals on this particular radio are not conducive to using the oscilloscope method, which is the same as a wobulator. All I do is I take the trigger out signal from the signal generator, and you can put that into one of the scope inputs, trigger it with that one, and I've done this before. I won't go into all that. The alternative is to use a signal generator, not a wobulator and not a scope. So what they suggest you do is you break the A+ line, in other words the 11 volt line here, you put it through an ammeter and you tune it so you get the maximum current draw. The logic is that when these circuits are resonating, they are drawing more current. Well, yeah, I guess you could do that. I've never done it like that. I normally go for the alternative, and there are 2 alternatives. One is you measure the AGC voltage, and the other one is you actually measure the audio output voltage, the AF, the level of the tone that you get on the output. And if you're sending in, say, a 600 hertz tone, the level of that tone will tell you just how well aligned these IFs are, because it means it's getting through optimally, okay? The AGC voltage method is a bit difficult here because it's got a pretty big capacitor in there, and that means that because the capacitor takes time to charge and discharge, it actually slows down the response. So it's not absolutely responsive. And so ultimately the best way is the simplest way, which is you measure the voltage at the output, AC voltage. You've got a tone coming out, which you can hear on a speaker. If you can hear on a speaker, it's actually an alternating voltage at 600 hertz. So if you measure that in an AC millivoltmeter or voltmeter, you can see when it's at a peak. Simple, right? That's exactly what I'm doing here. I've decided to go that route because it simply makes more sense to me, and everything is set up, and we can now just go through this. I've tried the other methods and I'm not too happy with the result. let me just tell you, I have not touched these guys. When I say I've tried the other methods, I've assumed that IF is getting through, and it is because we do have reception, right? So if we're getting IF coming through, I wanted to get a result on the scope, and I'm not happy with that result. It's very, very, very noisy, very low level. So I've decided to do it this way because I can hear the tone, right? So that's what I'm doing. The only thing I desoldered was this RF front end, and I'm feeding the signal generator, the ground to its ground, and the signal to the one end of a 4 picofarad capacitor. I'm going to switch on the signal generator. I've got everything ready, and I want to show you just to make sure that we can get a signal and that it's visible on the scope. In other words, if it's audible and visible on the scope, we know we can measure it with the AC voltmeter. The other thing they tell you to do is put this on sharp. Now you're trying to get this as sharp as possible. You put sharp selection on the front, and you put the volume on maximum so that you can feed in the smallest signal possible here and still get an audible signal and a measurable signal. And the idea being that the sharper it is, or rather the louder it is in terms of AF amplification, the smaller the signal you can put in here and the less effect the automatic gain control or automatic volume control will have on your measurements. So all is set, and I'm going to turn on the signal generator at 455 kilohertz with a 30% modulated 600 Hz tone. And it would help if I switched on the unit. And I can hear it. And if I switch off the modulation, I just get hiss. Switch on the modulation and I can hear it. Not only can I hear it, but I can see it. I can see it on the scope. Now, it's not a very strong signal. The signal I'm sending, the 455 kilohertz carrier that I'm sending in, is going in at 40 millivolts. And if I put it at 50, that's what happens. But I can see it at 40. I can actually see it at 30. I can still discern it as a sine wave. But 40 seems to be a good level, so I'll leave it on there. And now I'm going to connect up the voltmeter to the output. Now here's where we have to be careful. I've got the scope connected to one of the outputs. In other words, it doesn't matter which one, the ground, the negative or the positive. I have not connected the ground to the other side. And the reason is, this thing is push-pull. Neither of them is actually ground. And I don't want to create a ground loop and a short over here, so I have to make sure that whatever I connect on there, it's isolated from mains ground. And the reason is that my oscilloscope ground is connected to mains ground, and the signal generator ground is connected to mains ground, so it creates a bit of a confusion there. Now, the oscilloscope I connected across one side only, so I'm basically getting half the signal. This, however, is completely isolated, so I can connect it across the two, which is what I'm going to do now. So here we have it set up. I've got this on AC voltage, I've got this on 0.3 volts, and I'm going to switch on the modulation, and there we have it. I'm going to switch the dummy load to dummy so I don't have to hear it. I'm still seeing that half sine wave on the scope, just for my reference. Just to explain briefly, these coils here are the IF coils for the AM. Those are for the FM. This one here is the BFO, which we'll come to later. So the sequence they give you is that one, then that one, then that one, that one, that one, that one, that one. Then you go back and you do it all again. And when you do the broad, you switch the front to broad and you widen the bandwidth. That's if you want to adjust the shape of the curve. But at the moment, we want to increase the sensitivity, and I'm sure these guys have been fiddled with. So that's what I'll start doing. So there we are. We've got a reference value. Let me start. Oh, it's over here. This one first. No, wrong way. I'm using the wooden stick again so that we don't mess up anything over here. Whoa, Whoa! Okay, see what's happened here? That thing's shooting up and it still hasn't peaked. So I'm going to reduce the amplitude of the input signal to 30, actually to 20, and carry on. Now this should make a hell of a difference to reception. There we've peaked. Oh, that's nice. That is nice. I like it. Okay, top one. Wrong way. That one is pretty close. That one doesn't look like they messed with too much, if at all. I think maybe they just messed with that one, saw nothing was happening, and stopped. Please, I hope. So what I'm going to do is I'm actually going to skip these two and go to this one and see if they've messed with this one at all. No, no, that's at a peak. Next one. That's at a peak. Nope. Guys, I think that's done. I think they only messed with that one. And if these others were okay, then let's try and adjust this a little bit. That is the peak. That's one hell of a difference. That is one hell of a difference. This one hasn't been messed with at all. I'm loath to play with stuff that hasn't been touched. This has got wax on there. I'm not going to touch those. There's one thing you learn with these things, and that is leave well enough alone. Somebody came in here and tried that, got no results, and stopped. And that is brilliant. I like that idea. I like the fact that they've stopped. Okay, brilliant. Okay, I've made a discovery here. I had it peaked at 455, as you recall, and then I went to the signal generator and I put it at 456 and it went down, which is great. 457, 58, that's expected. Now, 455 is there, 454 went crazy, 453 went crazier, 452 jumps down. In other words, this thing is actually tuned to 453. And that means those two in the middle need adjusting as well. So I've actually removed the wax from those two, and I'm going to put this down to 10 millivolts. Well, actually, let me give it a bit more. 15 millivolts. So we've got that level. I'm going to try this whole sequence again. That's peaked there. That's peaked. This one is very finicky. There. That one we did. That's peaked. And that is peaked. All right. Now I'm going to do that one. See? I've got to come down, amplitude again. Reduce it to, what am I giving it? 7 millivolts. Because this guy hasn't stopped growing yet. Ah, there's the peak. Let me give it a bit more. 10 millivolts. Just makes it easier to peak it. There we go. And this one. Ooh, Got to bring it down. 6 millivolts. Oh, bloody hell. Look at this guy. I might have to use my attenuator after all. Yep, I definitely have to use my attenuator. This thing is just far too strong. That's the minimum I can get from my signal generator. Oh, there's a peak. There's a peak. Bloody hell, this is a huge difference. Huge. Let's start again. And there we go. Brilliant. That is one hell of a difference. There's 455. I'm bringing it down to 454. See that? 455, 456. So we are peaked at 455. And that's exactly what we want from this guy. That's good. That's our IF alignment done. Not much to it once you've understood what it is you're doing and why you're doing certain things and why you have to do a different way. I suppose now if I put the scope on there, I could probably get my signal, which before was so low I couldn't read it. And the reason was these guys were misaligned. And I don't understand how they managed to do that. I don't know how these guys were misaligned so much. I think perhaps this whole radio was actually tuned, aligned to 453 or whatever it was, instead of 455. And I'm not sure why. The only reason this could be the case is if, for example, the BFO was misaligned and they couldn't get it up to 455, so they could get it at 453. So what they did is they just aligned everything to 453. But that's not the way it's supposed to be. Okay, IF alignment, done. Now the last thing you need to align when you do this AM alignment, IF alignment, is you need to adjust the BFO. Now the BFO is switched on with a BFO switch at the front there. There's a switch and then there's a control, a pot. So the idea is when you switch it on, you're supplying power to it. You're supplying the B plus to it, the 12 volts or 11 volts to it. And it should start oscillating and creating a fixed frequency. And the volume control, or the pot, is to adjust the level of that carrier frequency, of that oscillated frequency that you're feeding into this IF chain over here. Now why do you do that? Well, if you want to pick up single sideband amateur radio transmissions, you need to provide your own carrier. And the carrier is precisely at the IF frequency, which should be if this thing's aligned properly. So what happens is normally you've got AM radio, it's got a carrier which is modulated with the audio on there, and it goes through there, and this thing follows it through, carries it through with the IF frequency, and then gets rid of the IF frequency and just leaves you with the modulated audio. With single sideband, they sort of give it to you without the carrier. They give you the information, but no carrier. It's like dried noodles. Bring your own water, you know, you save on shipping and things like that. What it does is it saves on transmission power because the carrier takes up a lot of power. Now, what it means is when you're putting that signal through here, you need to add the carrier, and the carrier should be at the same frequency as you would normally have in a receiver, which would end up being the IF frequency when it gets to the IF chain over here. So this thing should produce a 455 kilohertz carrier frequency, a sine wave, as clean a sine wave as possible. And it should be very stable. And you should be able to adjust it by a few kilohertz one way or the other with that call. And the way to do this really is, the way to adjust it is you feed in the carrier, just like we did with the normal alignments over here. But you don't modulate the carrier. You feed in just the carrier, 455 kilohertz, and that's a carrier wave with no audio modulation on it. and it goes through and then it meets this frequency. Now when you sum these two together, you will get two frequencies. One is the frequency sum of the two, and one is the difference of the two. So if this thing is exactly 455 kilohertz, what you get when you sum them is 910 kilohertz and 0 hertz. Now this is the trick. The 910 doesn't get through because the IF filters stop it. It'll only allow 455 to get through. The 0 hertz is different. It won't be exactly 0, and you can actually adjust it because you will hear the difference. The difference between the carrier and the IF frequency or the IF carrier that you're putting through there and the BFO frequency is going to be, let's say it's 2 kilohertz. Let's say this thing is at 453. You will hear a 2 kilohertz whistle coming through. If it's 2 kilohertz higher, say it's 457, you'll hear the same 2 kilohertz whistle. As you tune this closer and closer to 455, that difference becomes smaller. So that whistle drops in tone till it gets to the point where you don't hear it at all, which means it's less than 20 hertz difference. And when you go further the other way, you start hearing it because now the frequency difference is on the other side of the subtraction, if you know what I mean. So we should get a 455 kilohertz or thereabouts signal from this. And what we're getting is rather strange. Let me show you. Now when I switch on the BFO, this is what happens. It tries to oscillate, it comes on, and then it just dies. Off, switch on the BFO, and the frequency I can see is around 450, but I just need to adjust that core. So our BFO is fading to stay on. Right. And this is it over here. You've got all the components that are on that schematic crammed into this space over here with the tuning lug sticking out the top. There's that transistor. There are a few capacitors, a few resistors. And what you need to do is to make sure that you've got all the supplies on here. And I've done that. I've checked that ground is there. And I've also checked that the B plus is coming in. And the B plus comes in when you switch on the BFO. And I've checked that the B plus is coming in. So my guess is it's either that transistor or maybe something with the capacitors and resistors that's gone awry, and it just can't get the feedback that's required to do the oscillation. So I'm going to probably look at this transistor first, take it out and replace it and see what we get. We might just get lucky. Alright, I've got this all set up rather precariously. I had to short the can to the ground because that needed it. I've got the probe on this point, which I know is where the BFO comes out. And now I'll just focus on the scope and see what we get. I'm going to switch on the BFO. Ha! 1.27 volts RMS, 434 kilohertz. We should be able to tune that. Now I'm just going to tune that core. 440, 446. There we go, 454 and a half. I'll do the fine tuning once I put the cap on. I've got to put that cap on because this thing needs some shielding, but it's a very, very stable, or it seems to be fairly stable. Brilliant. One dead transistor, probably leaky. Okay, let me put this together and we can try and tune it. There we have it, we've got it back. You have to bend that capacitor back into place, make sure it fits. It's a tight fit. And I've soldered the ground lugs on the sides again. I've got the probe again on the output, And the way I'm going to do this is I'm actually going to tune it for about 455 first before I try and zero beat it against the carrier coming in. Okay, now there's nothing to guarantee me that this thing is going to be accurate once I remove the probe. It shouldn't be a problem. I've got 463. It's not accurate. I'm just going to get it close to 455, as close as I can. And it's probably not going to be that easy. Wrong way. Well, it's about close enough like this, and now I'm going to feed in the carrier. I'm going to try feed in the carrier just into there without desoldering that. We'll see if that works. This carrier will be a 455 kilohertz sine wave without modulation. We'll see if we can hear this thing zero beat or whistle. Okay, I'm feeding in a carrier. And as you can probably hear, you can hear the whistle there. Now that is not the modulated 600 hertz tone that I usually have there. That is the difference between the carrier coming in at 455 and the frequency that this thing's generating. Now watch this. It's getting closer, so the difference is getting smaller, so the tone is getting lower in tone. That is going up the other side again, so I'm going too far. So I need to get it back to where to where the frequencies are exactly the same, and it then is zero beating. I'm moving this very, very slowly. Ah, we've got it. Brilliant. I'm going to stop saying that. People are joking that I've got a set of phrases on my wall when I do these videos. Like, hi there, welcome back, and brilliant, and bloody hell. Even that comes out. Right, so we've got this thing aligned. The BFO is aligned. And it looks like all's good so far. Let's have a look at the other side and see if we can tune anything in here. Okay, here's an example. We're on shortwave 3, that is 16 to 20 megahertz. Put on narrow. Fine tune. Now if I put on the VFO, you can hear it sort of beat. Now if I tune it exactly, that means, you see I'm tuned away, I'm tuned in line. All this is doing is this radio, this station, is feeding a signal which has a carrier at 455, which is the IF that's produced, and it's meeting the BFO. So it's doing exactly the same thing as I was doing when I fed that carrier in there. However, we're nearing the end of the video for now, because there is another problem. You might find it suspicious that I got my finger up there. If I let go, there is still something wrong with those contacts on the barrel, and it's very annoying. See that noise? There it's receiving. So something is still wrong here. And if I go down, now it's on all of them. Earlier it was just on a couple of those bands, now it's on all of them. So there's still something short, not shorted, there's still a problem with the contacts on those barrel connectors. And it's not a cleaning issue, it's actually the bending motion, the pressure that those things are making in there. And I really am afraid to mess with that. I really am. If anybody's got any good suggestions as to how to tighten them without risking breaking them, I'd really appreciate it in the comments. And but for now, we've got the BFO working, which was completely dead, and we've got the IF alignment, and this thing is very responsive when it's not giving us contact problems over there. It's working a hell of a lot better. Much, much better. And the FM is fantastic anyway. But for now, I'm going to work on that barrel connector. I've got to sort that out, and I would appreciate your help. If you can just advise me, how do you tighten those things without taking them out and risking breaking them? Because that would be terrible. So that's where I'm going to end for now. I'll be back very soon. I've done all the studying I need to do. I think we're really close, really close to the end of this restoration. And it's been quite an experience. I've never opened up, I don't think I've ever worked with a solid state BFO before. Bloody hell. Learned something new. Again, one of those catchphrases of mine. Anyway, hope you've enjoyed this. Thanks for watching. And if you did like it, please click like, subscribe, click that bell thing on the subscribe so that you can get annoyed when I post another video. And if you want to support the channel, you can do so on Patreon. The link's at the end of the video. And I've been receiving quite a few supports or donations through PayPal. Thank you very much, guys. That link is also in the description below. And thanks for watching, and bye for now.